area, right? Yeah, we talk about the games in the last few days. We talk about the tic-tac-toe game. We talk about the min-max tree. Yeah, min-max tree. It's a game tree. Yeah. So what's special about this game tree is what? Do you still recall any of those? The game tree, the min-max. What's min-max?
1 min and 1 max.
That's a very good answer. Yeah. So one tries to minimize it. The other one tries to maximize it. Okay. So I'll give a few numbers and then. Let's discuss about this, okay? 3, 5, 6, 9. Okay, so here, if we want to maximize at this level, and we want to minimize here, okay? So I just give a portion of the tree. So what value should I put here? What value?
You should put 3.
The maximum,
No,
5, okay?
And then 9.
Okay, I put a 9 here, yeah?
Mm-hmm.
Okay, so now, okay, so this is the thing here. Come on, listen. Come on here.
Okay.
So look, if the game tree is evaluated from left to the right, yeah, from left to the right. Okay, look, this is the magic, yeah, left to the right. Okay, this is 5, I know, yeah. But this level, we're trying to minimize, yeah. Alright?
Yeah, sure.
So now, I have a value 5. So if this value is bigger than 5, then this value will be less than 5. That will be 5, right? Yeah? Make sense?
Yeah.
So if this value is smaller than 5, if it's smaller than 5, then the value will be smaller than 5. Am I right? The value, yeah? I said this is x. Okay? Yeah? Okay, so now x, we know we already have a 6 here. Yeah, we already have a 6 here. So we want to get x's maximum is at least 6. Am I right? So x is at least 6. Am I right? Make sense? Look. We have found a value 6 here. And at this level we're trying to maximize it. So x is bigger or equal than 6. Make sense? Yeah? X is bigger or equal than 6. And this level, we are trying to minimize it. We have 5, and then we know x is bigger than 6. What does it mean?
That means that's going to be 5.
Going to be 5. So does it really matter the values here? Does it really matter the values here?
No.
Look, x is bigger than 6. I know x is bigger than 6, right? So I don't need to visit this because I know x is bigger than 6. If x is bigger than 6, it can't be better than 5 because we are trying to minimize here. Got it? Because look, at this level, here, this value here, is the minimum of these two values. Am I right? And now, look, it's the minimum of these two values. So it's the minimum of 5 and x. But x is bigger than 6. X is bigger than 6. So what does it mean?
Means that's 5.
I have 5 now. I have x is bigger than 6, right? Yeah? So I don't have, do I have to visit this tree here?
No.
Why is that?
It's because you know it's 6 always bigger than 6, so
Yeah, it's this value, x is bigger than 6. No matter what value you put here, right? Yeah, if put 100, then it's bigger than 100. If this put -5, minus 100, this value is 6. Yeah? So if it's bigger than 6, so if it's a 6, and I want to get a minimum of these two, I have 5 here. Right? So I don't care what value in this tree. This could be a huge. This could be a tip of the iceberg. Yeah, tip of the iceberg. You could be.
that's not iceberg.
Yeah, I know. You know the tip of the iceberg. What does it mean?
It means you gotta jump off a cliff.
What does this meaning in English?
I don't know.
You know the iceberg?
Yeah.
You know the iceberg, the river, the ice, yeah? And then
Because you have luggage.
you have lots here.
They run like abload.
So the point is that we don't need to.
Power.
Yeah. So we don't. The point is what? We don't have to visit this bit. Yeah. and you will save us time, right?
Yeah.
This is one situation. How about the other one? How about let me just write another one, and you can tell me it's quite similar, okay? Okay, so let's see. We have values here, okay? The trees, game trees. The game tree evaluated from left to the right, okay? And it doesn't have to be binary tree. In fact, it could be many, depending on. This is one node is one game state. So one state you have a different moves, right? Yeah.
Mm-hmm.
Yeah. For example, for the tic-tac-toe, you have the branch factor could be 9. Why is that? At most. For the tic-tac-toe game.
Because there's 9 squares.
9 squares, yes. For starting from the root, you have 9 choice. You have 9 choice, right? Yeah. Okay, so now we have 5, 6, 4, 5, and then we are trying to do the minimize here. Yeah, we are trying to do the minimize and try to do the maximize here. Okay. So what's the mean here? What's this value?
5.
Okay.
4.
Okay. Again.
5.
Again. Okay. I'm trying to maximize here. So this is x. This is question mark. We're trying to minimize here. So I know there's a 4. So what's this value?
4. No.
X is what?
4 or less.
4 or less. Yeah, 4 or less. Okay, and I'm trying to maximize here. If it's 4 or less, the most is 4, right?
Mm-hmm.
Yeah? If it's most is 4, we have 5 here. Does it matter? It doesn't matter.
You do 5.
So that's 5 here. So what does it mean? So now I'm evaluating the tree from left to the right. Once I found this is 4, and I know this value is 5 here. Right?
Mm-hmm.
And I don't need to evaluate this subtree here. Do you understand? Look. Yeah? Yeah. So this bit, I can just cut it.
Mm-hmm.
Yeah? Do you understand what's cut it? Cut it, prune.
He said scissors.
What's this mean? Cut, prune.
Prune means those fishy things you eat.
What's cut?
And cut is like, yeah.
I just cut it. So if I cut it, it means that we don't need to travel. Yeah? We don't need to travel to it. Okay?
Mm-hmm.
Right? Yeah? Yeah? This situation and one I showed you before, yeah, is similar but different, right? So this one, look, this one is x smaller than 4. That one is actually bigger than what? Do you still remember? Actually, it's bigger than 9. Right? Yeah. The previous one example, yeah. Bigger than 6. Okay. Yeah. Yeah. Okay. So we call this algorithm call what? We call it alpha beta pruning. Okay. Alpha beta pruning. Yeah. So it's an improved version of the min max. So it will save us time. So it's alpha beta pruning. Okay. Alpha is it's like an A, yeah. Alpha beta is like a B, yeah. The Greek letters, yeah. Alpha beta pruning. So it's an improved version of min max. Yeah, min max we just exhausted all the branches. Yeah, one take exhausting. Yeah, the first player maximize, the other one minimize, and the next one maximize, minimize. It takes time, right? And now the alpha beta pruning is just remember the game tree. What we did is we stop searching a branch. Whenever we find it, it's useless to traverse the subtree. Why is that? Because no matter what score, yeah, on that branch, it will never be better than the current. Yeah, do you understand? To understand. Okay, so we can just add it in the min max algorithm. Okay, so let's write this min max first. Do you still remember min max? Yeah, that's yesterday. Okay, so I skip the cells. So we have a state. We have a depth, D for depth, and we have well, we have a 10, yeah? So instead of 10, let's make it, should we maximize it? We maximize it, okay? Maximize it, okay? Yeah? So let me just write it. So if it's ended state, okay? If the state is an end state, if state is end state, yeah? It's terminal, it's a leaf node, okay? It's leaf node. I'm just writing the pseudocode here. If state is the leaf node or is the state is the end state, then we can return the score of it, yeah? We can return the score, which is the utility function of state, okay? Now look, if we are maximizing it, then we need to go through the action. Yeah, we have a current score. Okay, so we have a score equal maximizing it, so that the beginning it will be the negative infinity, and then we go through the actions. Yeah, for actions in self.actions. Okay, we have a self.actions given the state, and then this actions function will tell me what possible moves in that. Okay, so then I will have a state, yeah, state, new state. This is from yesterday. New state equals the successor of the state and then the action. Okay, state and action. And we are maximizing, since we are maximizing, so the current score equals min max new state. We are going down. We make one move. So the t will +1 because this next level, and then we are maximizing in this one. So the next one will be what? Minimizing. So will be, if this is maximizing, okay, then we say minimizing is false. Okay, we can just say false. Okay, and then now if current score is bigger than score, this is the best score so far, and then score equals current score, and then return score. Okay, else is the minimizing. Okay, this is quite similar except that we change the sign, right? We are minimizing it, so we should change this to true, and then current score should be score, right? So now, we can make changes in here to make it alpha beta. Okay, so first thing is we need to pass two value, which is alpha and beta. Okay, so alpha and beta. Okay, and at the beginning we passing this alpha beta, it will be like this is window, right? Alpha basically defines the left boundary, beta is the right boundary. Yeah. So it's like a window. So here is alpha. This is beta. At the beginning, we give a parameter minus negative, and then positive infinity. Yeah. At the beginning, we give a value, meaning that the score will fall in this range, right?
Yeah.
So if we keep searching that, then we can push these boundaries towards each other. We can keep updating it, right? So how do we keep updating it? So we can do what? We can first of all we can have this. So here will be alpha will be maximum alpha of the value. So if I put it here, okay, alpha, then I can change alpha equal. I will keep updating because this is trying to push, doing the maximize. Yeah? So alpha equals max alpha, and then value will be current state, current score. Okay, alpha equals this. The thing is that if we keep updating the alpha, and then if the next one is smaller than the alpha, what does it mean? So if I can say, if current score is smaller than alpha, then I can just quit it. Because what? Because we are trying to maximize here, right? We are trying to maximize here. So first of all, let me just change it to alpha beta. Alpha beta, okay? So here will be alpha beta. So I'm trying to maximize. So look, we are trying to maximize here. Yeah. the maximize. We're trying to maximize it. So look, if the value, if the current score is bigger than beta, then I can just break. Okay, I can just break. Okay, and then return the score here. Return the score. This is the maximizing it. So look, we are trying to maximize it, and then if the current score is bigger than the score, we update the score, right? But also we push the boundary, the left boundary, alpha boundary, to the right. Okay? So we are pushing the boundary. But in some case, the value, the value is bigger than here, right? If the value is here, outside the boundary, so then I can just break it, right? This is we call it the beta pruning, because it falls on the right boundary of beta, so we just stop it, because there's no point to keep searching in this here, right? Yeah. Okay, so the other case is if minimizing it, right? So this will be the same, except if this is minimizing it, okay? Let's say if I say if this is minimizing it, okay, minimizing it. Score will be the positive, positive infinity. And then I will change this to true, right? Because the next one will be maximizing it, right? Right? And if current score is smaller than the score, I updated the current score. And then you look here, will be minimizing it, but instead of alpha, we need to the mean equals beta equals mean beta current score, right? And if the current score is smaller than alpha, smaller than alpha, okay? Actually, boundary doesn't matter. If you put an equal, that should be okay as well. If score smaller than alpha, then we break it, return the score. So what does it mean here? If the score falls on the left boundary, the alpha, right? Because we are now, at this case, we are minimizing it, and we're pushing the beta boundary to the left, right? And if the value falls on the left-hand side of the alpha, it means that we don't need to continue, right? Yeah? Make sense? Okay, so this is if minimizing it, if you're minimizing, just this minimizing, if you're minimizing, okay. Okay, so any questions so far? Why are we doing this? Why are we doing this? Any question?
Not really.
So what did they talk about?
You talked about the game tree.
Yes, and then today. So,
but we're doing one of the min-max.
yeah, and then we are using this technology. Yeah, so the alpha beta needs another two parameter which we need to pass. Yeah, alpha beta. Okay, and we at each round, depending on whether we are maximizing or minimizing, we need to keep updating the boundary, right? Keep updating the boundary, which is alpha, beta. Alpha is the left boundary, beta is the right boundary. And once if the current score is either falls on the left-hand side of boundary or falls on the right-hand side of boundary, then it means that we can just stop searching in that branch. Right? Why is that? Remember, we talked about that value, yeah? 3569, yeah? 3569. Okay. Okay, yeah. So, can you tell me whether this one is so here this is the 5, yeah. We want to get the maximum here, right? And then here will be, the minimum, right? Minimum, right? Again, let's talk about it again. 5. This is 5. 6. I know this x value is at least bigger than equal than 6, yeah. Yeah. I haven't explored this bit yet, but I know from here I said this value x could be bigger or equal than 6, right? Yeah? If it's bigger or equal than 6, because this level is trying to minimize it, we have a better value 5 here. Yeah? So it means that we don't need to explore this. Yeah? Because there's no point to explore this. It doesn't change the value of this here. Eventually I want this value here. This value is 5. I know how to fill this value 5 without exploring it. Make sense? It doesn't change. Here it doesn't change. Why is that? This is maximum with 5. Here is 6. I want to get the maximum. So this value x is bigger than equal than 6. Right? If it's bigger or equal than 6, it doesn't change the result 5 here. Because we got a better result, a better value 5 here. This is looking for the minimum. Make sense? Yeah? So look, this value is bigger than equal than 6. So this one will be terminated. So there's no point to keep doing that, right? There's no point to keep doing it. It means that this boundary is what? 6 bigger than equal than 6, right? So x is bigger than equal than 6. So we have a boundary. So which one is the alpha, which one is the beta? Which one is the beta, which is alpha? So x is bigger than equal than 6. Yeah, x is bigger than equal than 6. Yeah. So I think this is the right boundary, yeah? Because it's forced on the right boundary, so there's no point to continue. Okay? Yeah?
Yeah.
Okay. So there's another thing to notice is that you can put this break after the updating the boundary or before the updating the boundary. If we updating after the boundary, so the result, this whole result will be, there could be possible the value will be outside, yeah, the return value could be outside the boundary, so we call it fair soft. If we put this before updating the boundary, then the value returned will be strictly inside, we call it fair hard. Make sense? So it's just this one, beta, and then this if statement. If statement is to break, to terminate, right? To terminate, right? So if we switch the order, that will make a difference, right? So sometimes the value will be so to visualize it is that you are here, right? Yeah? Alright? So if the result value is here, is within this boundary, then it's fair hard. Because you can't always go outside, right? Okay. But if you say, okay, you move outside, and then you realize you're outside, but you return this value, we call it fair soft. Make sense? Because you're outside the boundary, right? You return that as a value. That's the difference. Okay, let's call it fair soft, and then fair hard. Okay. Okay. So with this alpha beta, which one is better, alpha beta or min max? Which one is faster?
Alpha, beta.
Yeah, we're done because we have a check. If it's 4 outside, we just stop searching and you will accelerate the search. Without this, the game tree could be huge, could be enormous. Yeah. So it will take time. Yeah. Remember, it will be like something like so it's another technique to speed up the searching. Yeah? Remember in the Fibonacci number, yeah, we use the cache to remember the values we have calculated, so we don't calculate again and again, right? So that's another technique to speed up the search, right? Make sense? So instead, this is a slightly different. Instead of remembering the value for a node, we just discard it because we know there is no point to exploring the subtree. It doesn't change the outcome. Why do we need to waste time calculating, spending time in the subtree, knowing that it doesn't change the result? Yeah? Okay, so what have you learned today? What's the most important takeaway you take it?
Alpha, beta.
Alpha, beta.
Prawn.
Okay, can you explain to me about this?
When you do the maximum of 3 and 5 and 5.
Yeah, okay.
Yeah.
Okay, now 6 and And no matter what happened here, 6.
When you visit 6, yeah, it must be 6 or over.
Yeah?
But then since 6 is, the minimum is 6, and 6 is already over 5, so we know the minimum on the overall result is 5.
Well done. Yeah, I know you know it. Yeah? Keep practicing your presentation skill, but I know you understand, okay? That's it for today. Bye-bye.
Bye.
Bye-bye.